So AC circuit having a resistor only, that's the first circuit. So in every circuit, your motive is to calculate the equation of current. Using equation of current, you are supposed to calculate the phase difference, the average power, the power factor, and everything. So the first thing is AC circuit having resistor only. So let's take a resistor. The resistance is R. Connect it to an power supply. This is AC supply E naught sine omega t. So the equation of EMF is given. You're supposed to calculate the equation of current. While calculating equation of current, you will get phase difference. When you have phase difference, you can calculate power factor and obviously average power. So the equation of current is see, for resistor you can use Ohm's law. So the equation of current is I. Current is EMF divided by resistance. So your EMF is it's E naught sine omega t divided by resistance. See, EMF divided by resistance is current. If I divide peak value of EMF by resistance, then the equation that you get is peak value of current, I naught. So if I substitute this thing here, the equation of current comes out to be, I call this as equation number 1. I call this as equation number 2. The equation of current comes out to be I is I naught sine omega t. This is the equation of current, equation number 3. So this is the equation of current, I naught sine omega t. Okay, Fatma, if you compare equation number 1 and 3, can you tell me what's the phase difference between them?
0.
0, right? Yes, Afroza, phase difference between E and I. See, the phase of EMF is omega t, the same phase of I is omega t, both have same phase. You'll get that phase difference between them. Phase difference between E and I is 0, right? Because both are in same phase. So I can write your phase difference as phi, so it comes out to be 0. That's the phase difference. So once you have phase difference, you can calculate power factor. Padma, do you remember what is power factor? How to calculate power factor? Power factor we did in the last class, that power factor is cos phi. If I put phi equal to 0, then power factor is cos 0, it comes out to be 1. So power factor for a circuit having only resistor is 1 only. After power factor, you're supposed to calculate average power. Say average power here is P average. The expression of P average is it's E RMS, it's I RMS multiplied by cos phi. If I substitute all these values, then P average comes out to be E RMS, I RMS, cos 0. Cos 0 is 1. So this is the average power, which is E RMS multiplied by I RMS. So in a circuit having, if you connect a resistor through an AC supply, then the peak value of current is this, E naught by R. The equation of current and equation of EMF, if you compare them, the phase difference is 0. They are in same phase. The power factor between them is 0. So power factor is basically cos phi. Where phi is 0, just put phi equal to 0, it's 1. Average power dissipated is ERMS, IRMS into cos phi. I'm substituting the value of phi here. So it comes out to be ERMS, IRMS. The next thing is you need phasor diagram. The next is phasor diagram. You need phasor diagram. We did phasor diagram in the last lecture. So for phasor diagram, just take an arrow. So again, for phasor diagram, I'm drawing first the phasor diagram of E naught sine omega t. I'm drawing phasor diagram of this term. E is E naught sine omega t. So to draw this phasor diagram, take an arrow. First of all, this phasor diagram is not a graph. We did it yesterday. We discussed yesterday. It's not a graph. It's a diagram. In this diagram, take arrow, one arrow equal to the peak value. The peak value of EMF is E naught. So take an arrow. The length is equal to the peak value of EMF. So I take an arrow. The length of the arrow is equal to peak value of EMF. The inclination of that arrow with the x-axis is this phase, omega t. So the inclination of the arrow with the x-axis is this omega t. So that is the phasor diagram of E naught. After phasor diagram of E naught, you can draw phasor diagram of current. The equation of current is I naught sine omega t. So again, take one arrow. The length of the arrow is equal to the peak value of current. The inclination with the x-axis is this omega t. So I take another arrow. The length of the arrow is I naught. And its inclination is same omega t. So from this diagram, it's very clear that current and EMF are in same phase. There is no phase difference. So I'm taking, if you're drawing phasor diagram of this term, E is equal to E naught sine omega t. E naught is the peak value. So take one arrow. The length of the arrow is equal to E naught. The phase is this omega t. The inclination with respect to x-axis is this omega t. So there is no complication in this diagram. It's a straightforward thing. Take one arrow equal to E naught. The inclination of this arrow with the x-axis omega t. That's it. Take another arrow. The length is equal to I naught. Inclination of this arrow with respect to x-axis is again omega t. So that's the phasor diagram. So both EMF and current here are in same phase, exactly in same phase. This is clear from the diagram also, and even in theory, we have calculated that phi equal to 0. After phasor diagram, there's one more thing. You're supposed to calculate the sine curve. The next is sine curve. See, the equation of EMF is E naught sine omega t. You know how to draw the sine curve. This is time. This is EMF. This is the graph. This is for the EMF. This is EMF. Then for current, the equation of current is this. I is I naught sine omega t. So for current is again the variation is sinusoidal, but peak value of current could be different from the peak value of EMF. So the first one is for EMF. The peak value of EMF is E naught. The second one is for current. This is for current. The peak value of current here is I naught. This black one is for EMF. This one is for. This one is for EMF and the red one is for current. So the sine curve means just plot EMF versus time graph and current versus time graph. So here both EMF versus time as well as current versus time, they are sinusoidal function. So the graph would be sinusoidal. Both are sinusoidal functions. Just their peak values are different. Okay, let's do one numerical on this concept. So you have a resistor of 10 ohm is connected to AC supply And AC supply is this. E is equal to 20 sine 314t. This is the AC supply. E is 20 sine 314t. Calculate first part. Peak value of current. Peak value of current. I'm giving hint alongside. Peak value is E naught by R. I naught will be E naught by R. Second, I need RMS value of current. So once you have peak value of current, using that peak value, you can also calculate the RMS value. Third part. After RMS value, the next thing that you have to calculate is not average value. I need power dissipated. Power dissipated across R. And the fourth is equation of current. The fourth thing that I need is equation of current. Let's solve it, the first part. The peak value of current is basically the peak value of EMF divided by resistance. So I naught is just E naught divided by R. So if I compare here, E naught is 20, R is 10 ohm, it comes out to be 20 by 10, it's just 2 ampere. Second part, RMS value. Afroza, if you have peak value of current, how do you calculate the RMS? Afroza, just check the notes of the last lecture. We have done plenty of numericals on this thing. You need not integrate. IRMS, we derive directly that it's I naught by root 2. So IRMS is 20 by root 2. Clear? Third one, power dissipated. For power dissipated, you can write this as average power dissipated in resistor is ERMS into IRMS into cos 0 because phase difference is 0. I have IRMS. Achha, sorry. I naught is 2. Yes. So IRMS is root 2 ampere. Average power is ERMS, IRMS into cos 0. Afroza, how would you calculate ERMS? You have E naught to be equal to 20. How would you calculate ERMS? Afroza. It would be better if you can use your mic. That would take less time. Yes, good. E naught by root 2. So ERMS is E naught by root 2. So your E naught is 2, root 2 is root 2. It comes out to be root 2 volt. So if I substitute all values here, that your P average ERMS is root 2, IRMS is root 2, cos 0 is 1, then you will get that your average power is 2 watt. This is the average power, 2 watt. After average power, the fourth is you need equation of current. The equation of current is this. E is E naught sine omega t. This is the equation of current. E is E naught sine. Sorry. This is EMF. This is the equation of current that I is I naught sine omega t. This is the equation of current. How much is I naught? I naught we have calculated. It's 2 ampere. So I naught is 2 sine omega, which is 314 into t. Let's do one more question on the same concept. I'm just changing the numerical values. Calculate and report your answer. E is 10 sine 100 t volt. Calculate first part. Average power dissipated. Second. So you have peak value of EMF, which is 10 volt. Resistance is 5 ohm. The peak value of current is E naught by R. So E naught is 10, your R is 5, it's 2 ampere. That's I. So once you have I naught, you can calculate IRMS. IRMS is I naught by root 2. So that's basically 2 by root 2. Okay, Afroza. Now you are correct. IRMS is root 2 ampere. Your ERMS is E naught by root 2. So that's 10 by root 2 volt. Average power, the first part, is ERMS multiplied by IRMS multiplied by cos 0. ERMS is 10 by root 2. IRMS is 2 by or root 2. Cos 0 is gets cancelled. Average power is 10 volt. The equation of current is I naught sine omega. I naught is 2 sine 100t. So this is about AC circuit having only one resistor. The next thing is AC circuit having inductor only. AC circuit having inductor only. In this topic, we will use electromagnetic induction. We will use the concept of inductor. So I take an inductor. The inductance is L. I connected this inductor to an AC supply. AC supply is E naught sine omega t. So you have equation of EMF, you need equation of current. See, inductor is not resistor. For inductor, you cannot use that your current is E by R. Inductor doesn't have resistance. You need some other equations to calculate current. In inductor, current is not E by R. There is no resistance in inductor. Inductor works on the principle of self-induction. So for inductor, there is induced EMF in the inductor. Induced EMF in inductor. That is E, which is minus of L di over dt. This we did in self-induction. So you have two voltages basically. One AC voltage that you have applied, another induced EMF in the inductor. Does any one of you remember Kirchhoff's second law, Kirchhoff voltage law? Any one of you remember what is Kirchhoff voltage law? KVL. Kirchhoff voltage, I'm using KVL. I'm using KVL, which is Kirchhoff voltage law. So Kirchhoff voltage law says the algebraic sum of all the voltages in a closed loop is zero. So you have two voltages. One voltage is EMF, another is induced EMF. So I can write this as E plus E is equal to 0. That's my second equation. I can substitute the value of E from here. I can substitute 1 into. If I substitute 1 in 2, it comes out to be E minus L di over dt is equal to 0. You can take this to the right hand side. You can write this as E is L di over dt. I'm multiplying this dt here. So you get E dt is equal to L di. So you have current di in a small time dt. You need current for any time. So you can integrate on both the sides. So on integrating this equation, like I'm integrating E dt here, and I am integrating L di. This E is basically this equation of EMF. So this E, I can write this E as it's E naught sine of omega t. I can substitute E here. So this is E naught sine omega t dt is integral of L di. See, you don't have limits in this integration. We are not doing definite integral here. We are using indefinite integral here. Integration without limit. So the next thing is this is integral of L di is equal to integral of E naught sine omega t dt. You can take this L outside. If you take this L outside, that's integral of di. L di. And this you can take this E naught outside. When you take this E naught outside, this is sine omega t dt. If I integrate this dli, the integration of di is I. This is E naught. If I integrate this sine omega t, this we did yesterday. That integral of sine omega t is minus of cos omega t by omega. Plus one constants. So whenever you integrate it, when you integrate to indefinite integral, instead of limit, you just write a constant c. So your Li comes out to be minus of E naught by omega cos of omega t. So this is plus c. So the equation of current is it's minus of E naught by omega L. I'm dividing it L here, cos omega t plus c. This c by L. This c is a constant of integration. Whenever you do indefinite integral means integration without limits. Limits are not given here. So in indefinite integral, you will get a constant c. We will later calculate what's the value of c now. I call this as equation number. We did two equations, one number, two number. This is equation number 3. Now, this constant of integration is 0. I'm not deriving why it is 0. It can be derived using the concept of average velocity for full cycle. Sorry, average value of current for full cycle. So I'm not deriving it here. I'm just writing its value directly, that C is equal to 0. So your I comes out to be, it's minus of E naught omega L cos omega t. Now, the next step is you have to convert this cos omega t in terms of sine omega t. Because your EMF is in terms of sine. So suppose to convert your current also in terms of sine. So you can write your cos omega t as, you can write cos omega t as sine pi by 2 minus omega t. So if I substitute instead of cos omega t, if I substitute sine pi by 2 minus omega t, the equation of current is now minus E naught by omega L It's sine of pi by 2 minus omega. It's E naught by omega L. You can just multiply this negative sign inside. It's minus I by 2 plus omega. So it's E naught by omega L. So I'm just multiplying this negative sign inside. E naught by omega L sine omega t minus pi by 2. That is equation number 4. So you have EMF is the equation of current is E naught by omega L sine omega t minus pi by 2. So this is the equation of current. I is E naught over omega L sine pi by 2 minus omega t. If I compare this thing with the current, with the equation of current, the standard equation of current should be, I'm calling this as equation number 4. I'm just rewriting equation number 4, okay? Standard equation of current is I is I naught sine pi by, or not pi by 2 minus omega t. It's omega t minus pi by 2. Omega t minus pi by 2. Fifth equation. Afroza, can you just tell me what's the value of I naught in fourth if you compare this 4 and 5? Yes, E naught by omega, right? So your I naught is E naught by omega. Usually we write current as E naught by R. Usually we write current as E naught by R. But now I'm writing current as E naught by omega L. Afroza, what value are we using instead of R? What value are we using instead of R? Good, omega L. So basically here in this circuit, this omega L is analog of resistance. It's playing the same role for inductor what the resistance plays for resistor. It's playing the role of resistance here. We call this omega L, we represent this omega L by XL, and we call XL is inductive reactance. We call that this XL is inductive reactance. No, we cannot write omega L equal to R. See, what is omega L? I'm coming to it. XL is inductive reactance. Your XL is equal to omega L. So physically, this XL represents the obstruction offered by inductor in the flow of current. It represents XL represents obstruction offered by inductor in flow of current. Obstruction offered by in the flow of current is given by XL. See, there is difference between resistance and XL. These are analog. Like in straight line motion, you use velocity. In rotation, you use angular velocity, right? In the same way, these are analogs. Yes. In a circuit having resistor, resistance shows basically the obstruction offered by the resistor in the flow of current. But in a circuit having inductor, This inductive reactance basically shows the obstruction offered by inductor in the flow of current. Both are showing obstruction, but the mechanism are totally different. Resistance is due to collision of electrons and ions. This we did in current electricity. But here, this inductive reactance is due to self-induction. Due to self-induction current, this inductor oppose the change in strength of current through itself. So these are analog. It's not equal to R. Mechanism are different. So in this equation, if I substitute XL instead of omega L, I will write this as I naught is equal to E naught divided by XL. This is I naught, which is E naught by XL. This is peak value of current, which is peak value of EMF divided by inductive reactance XL. So in resistor, the peak value of current was E naught by R. Now this is E naught by XL. The SI unit of XL is just like resistance, its values. So I'm repeating again, it is not resistance. You cannot write omega L is equal to R. It's wrong. Because XL and omega are defined for two different circuits. They have totally different mechanism. Resistance is due to collision of electrons and ions. Inductive reactance is due to self-induction. Okay, so after I naught, I can this is equation number 5. This is I naught. If you want to calculate IRMS, you can even calculate IRMS as ERMS divided by XL. So after getting the equation of current and the equation for peak value of current, you need phase difference. You need phase difference. So the equation of EMF and current are equation of EMF and current are the equation of EMF is this, it's E naught sine omega t, and the equation of current is this, it's I naught sine, it's omega t minus pi by 2. This is the equation of current. So if I compare these two equations, it's very clear these two are not in same phase. They have a phase difference of pi by 2. In fact, it's very clear that current lags behind by EMF by a phase difference of pi by 2. So here current lags behind by EMF by phase difference of pi by 2. So here the phase difference is pi by 2. So EMF and current here are not in same phase. They differ by a phase difference of pi by 2. The next thing is just draw its phasor diagram. So when you draw phasor diagram of EMF, you will take an arrow. The length of the arrow is equal to the peak value of current E naught. And the inclination is with the x-axis is omega t. So this is the length of the arrow. The length of the arrow is E naught. And its inclination with the x-axis is omega t. This is it. Next, you have equation of current. The peak value is I naught, but inclination is omega t minus pi by 2. Minus pi by 2 means it will go in the fourth quadrant. Current will lag behind the EMF. So it will go in the fourth quadrant, that's I naught. This phase difference is pi by 2. Is it clear? This angle is omega t pi by 2 minus omega t. So this is the phasor diagram. From this phasor diagram, it's very clear that current lags behind by EMF by a phase difference of pi by 2. After this phasor diagram, the next is power factor. See, power factor is cos pi by 2. Cos pi by 2 is 0. That's power factor. Then you need average power. The average power dissipated is ERMS, IRMS, cos pi by 2. This is it. So power factor is 0, average power is 0. So this type of current which have 0 power dissipation is known as wattless current. So current through ideal inductor is wattless. Wattless means there is no power dissipation. Power dissipation is 0. This type of currents are known as wattless current. Okay, after power factor, the next thing is we're supposed to calculate the sine curve, simultaneous sine curve. See, the equation of EMF is this, it's E naught sine omega t. The equation of current is this, it's I naught sine omega t minus pi by 2. So to draw sine curve, it's better to convert this sine into cos. I can take a negative sign. Basically, I'm doing the back calculation. If you can remember here, we have converted this minus of cos omega t into sine omega t minus pi by 2. So I'm doing the back calculation. I'm returning back to minus of cos omega t. I'm going back to minus of cos omega t. So I'm writing it here like I'm taking a negative sign common. If I take negative sign common, that's minus of I naught sine pi by 2 minus omega t. And you know that sine pi by 2 minus theta is cos theta. So that's I is minus of I naught sine omega. So this is equation, oh, sorry, not sine, cos omega t. So to draw the diagram, I will use sine as well as cos. For EMF, I will use sine, and for current, I will use cos. Now see how these graphs look like. See, this is sine curve, right? We have used this many times now. This is cos. The cos will go like this. Because at theta equal to 0, cos 0 is not 0, cos 0 is plus 1. So it goes like this. But here, I will not use cos. I will use minus of cos. So minus of cos means this graph will get inverted. It will be like this. Minus of cos means this graph will get inverted. It will be like this. So this is for cos and this is for minus cos. So if I draw sine curve, for EMF, I will use the same usual sine one, sine graph. So this is time. This is the graph for EMF. This is the peak value, E naught. But if I draw the same thing for current, then current depends upon cos with a negative sign. So the graph will go like this. This is for the current because it's not cos, it's minus of cos basically. So, and this is the peak value of current at sine. So this is the sine curve. Basically, these curves, these phasor diagram that I am doing, these are numericals or conceptual questions. I'm discussing everything in theory. After the sine curve is there's few conceptual questions on self-inductance, not self-inductance, inductive reactance. See here, inductive reactance XL is equal to omega L. So if I plot a graph between XL and omega, this is omega and this is XL. This graph will be a straight line. It's a straight line graph, linear graph. Okay, can you tell me what the slope of this graph will represent? If I say this angle is theta, what the slope will represent? See, slope of this graph will be equal to tan theta, right? And what is tan theta? It's perpendicular upon base. The perpendicular is parallel to base is parallel to omega. So this is XL divided by omega. And how much is XL? XL is omega L divided by omega. It gets cancelled out itself. So the slope of this graph basically represents L, self-induction. Afroza, I'm repeating it again. Next, we are discussing some conceptual questions on inductive reactance. XL is omega L. XL is directly proportional to omega. So if I plot XL versus omega graph, this graph would be a straight line. Next, he can ask the slope of this graph. The slope of the graph is tan theta. It's perpendicular upon base. Perpendicular is parallel to XL. Base is omega. XL by omega, it's L. So slope is equal to. That is inductive reactance. After this graph, you can even write this as 2 pi nu L, where nu is frequency. So now, if I plot XL versus frequency graph, so again, linear graph will be a straight line. Fatma, what would be the slope of this graph now?
2 pi L.
2 pi L, right. So it's basically XL by frequency. XL is 2 pi nu L by mu. See, L is not length, L is self-induction. It's 2 pi L now. So XL is omega L. Tell me, I'm giving you two circuits. For one circuit, XL, the value of XL is 10,000 ohm. For another circuit, the value of XL is 0.001 ohm. Which circuit? This is circuit number 1, this is circuit number 2. The current in circuit 1 is I1, the current in circuit 2 is I2. Which current will have higher value? 2, right? Smaller the obstruction, greater would be the current. Now see what type of conceptual questions you can get on this concept. XL is equal to omega. So I'm first checking the behavior of this inductive reactance for a system having very high frequency. Let's say you have a very high frequency X circuit. So you have a very high frequency AC. If you have a very high frequency AC, that means your omega is large, very, very large. If your omega is large, that means XL is large. For a very high frequency AC means omega is large. Omega is large, that means XL is large. If XL is large, that means your current, which is basically E by XL, I is small. I small means your inductor will not allow the current of very large frequency to pass through it. If you're passing a current of very high frequency through an inductor, then its inductive reactance would be very high. It will try not to allow that current to pass through it. So inductor will not allow high frequency current to pass. Now, if you, instead of high frequency, you have a very low frequency AC, that means your omega is small. If your omega is small, that means your XL is small. If your XL is small, then I is E by XL. That means yours I is large, your current is large. Now, if your current is large, that means this will allow, the inductor will allow the small frequency to pass through it. Hence, inductor will allow small frequencies to pass. This is it. So inductor will not allow any large frequency to pass through it, but it will allow small frequencies to pass through it. Okay, now solve this numerical. It's a lengthy numerical. An inductor of 10 Henry is connected. This is L, self-inductance. AC supply is 20 sine 314 t. Calculate first part. Inductive reactance. This is basically your omega. Instead of 314, take some another value. Take it to be 10t. That's your omega. Next, I need peak value of current. Next, I need equation of current. Last, I need power dissipated. See, your L is 10 Henry. The omega here is 10 radian per second. XL is omega L. So your omega is 10, your L is 10. So your XL is 100 ohm. Fine, Afroza? It's 10, na? It's 10t. Okay. For the second part, the peak value of current is E naught divided by XL. Here E naught is 20 and XL is 100. So it comes out to be 1 by 5. Equation of current. See, in this circuit, the equation of current is current lag behind voltage by a phase difference of pi by 2. So keep on substituting the values. Your I naught is, how much is I naught? I naught is 1 by 5. It's sine. Omega, how much is omega? It's 10t minus pi by 2. So this is the equation of current here. After the equation of current, the next thing is the fourth one. You need power dissipated. The average power dissipated is this: ERMS, IRMS, cos pi by 2. Cos pi by 2 is 0. So your average power dissipated is 0. Is it? Okay. After this inductor, the next circuit is AC circuit having capacitor only. AC circuit having capacitor. So this is a capacitor. This capacitor is connected to an AC supply. Capacitance is C. The AC supply is this, is E naught sine omega t. E naught sine omega t. So you need equation of current. For capacitor, you need equation of current. So even for a capacitor, you cannot use Ohm's law because for capacitor doesn't have any resistance. You cannot write your current as E by R. Just like inductor, you have to think some indirect method to calculate current. Sure. So now, just like resistor and inductor, we have third circuit, that is AC circuit having capacitor only. So this is a capacitor. You connected this capacitor to an AC supply, which is E naught sine omega. So you can write this as charge stored in capacitor. So do any one of you remember what is the formula to calculate charge in the capacitor? You have a capacitor C connected to an AC supply of EMF E. C, charge is Q is equal to CV. This we did in capacitors, right? Q is equal to C. So if I substitute the value of E here, the charge comes out to be C E naught sine omega t. That's equation number 2. So now you have equation of charge. If you have charge, how would you calculate current? Have you read this formulas ever? Have you heard about this formula that current is rate of flow of charge? So that's basically the relation between current and charge. If you have current, if you have charge, differentiate that charge with respect to current and you will, with respect to time, and you will get current. So current in the circuit is, current I is dq over dt. Next I am substituting q to be C E naught sine omega t. So that's d over dt of C E naught sine of omega t. It's C E naught, it's d over dt of sine omega t. So I is C E naught, it's sine omega t. So when I differentiate this sine omega t, this will be omega into cos omega t. The derivative of sine omega t is omega into cos omega t. So this is the expression of current. I is CE, or it's omega CE naught cos omega t. Next. So this omega c, I'm writing this omega c as 1 by omega c in denominator. This will not affect your equation. You can take this omega c in the numerator, we'll get back the same equation number 3. So there's E naught by 1 by omega c cos omega t. Next, you can write your cos omega t as a sine omega t plus pi by 2. This is again basic trigonometry, that sine omega pi by 2 plus theta is equal to cos theta. Instead of this cos omega t, I'm writing sine omega t plus pi by 2. So if I make the substitution here, your current I comes out to be, it's E naught divided by 1 by omega c sine omega t plus pi by 2. Okay, Afroza, just tell me, in this equation, what is I naught? Alright, great, good. This E naught by 1 by omega c is I naught, huh? Yes, yes. I naught is E naught by 1 by omega c. Now, just like inductive reactance, we will define this term as capacitive reactance. Okay, good. So the next thing is, now I'm defining, so this is equation number 4, that I naught is E naught by 1 by omega c. This is equation number 4. Now I'm defining capacitive reactance. I'm defining capacitive reactance. Capacitive reactance Xc is 1 over omega c. That is Xc. Capacitive reactance Xc is 1 by omega c. This is it. It's SI unit is again ohm. SI unit is ohm again. I call this as fifth. I can substitute 5 in 4. If I substitute 5 in 4, your I naught comes out to be E naught by X. So this is basically the obstruction offered by capacitor. That's equation number 6. Next, what we can do is, in this equation, it's better to substitute it here. If I substitute it here only, then your equation of current is I naught sine omega t plus pi by 2. This is my equation of current. And this is the peak value of current, and this is the formula of capacitive reactance. So now you have equation of EMF as well as equation of current. Okay, the next thing that I need is the phase difference. The next thing that I need is phase difference. Equation of EMF is, this is the equation of EMF. It's E naught sine omega t. The equation of current is I is I naught sine omega t plus pi by 2. So now if you compare these two equations, you will get that they are not in same phase. In fact, current leads EMF by a phase difference of pi by 2. Current leads EMF by phase difference of pi by 2. This is it. Current leads EMF by a phase difference of pi by 2. This is it. Next, we need phasor diagram. Next, we need phasor diagram. So the equation of EMF is this E naught. This is omega t. Current leads EMF, right? So this is current. Current leads EMF by a phase difference of pi by 2. This is I naught. This phase difference is pi by 2. This is the phasor diagram. After phasor diagram, you can calculate all those things. Like you can calculate power factor. Fazan, can you guess how much is power factor now? Power factor is cos pi by 2, which is 0. So just like inductor here, power factor is 0. Next, you need average power dissipated. Average power dissipated. Here too, the average power dissipated is ERMS, IRMS, cos pi by 2. The average power dissipated is 0. The average dissipated power is 0. Okay, the next topic is sine curve. The next thing is we need sine curve. See, the equation of EMF is usual E naught sine omega t. The equation of EMF is usual E naught sine omega t. But the equation of current is I naught sine omega t plus pi by 2, which is basically cos omega t. For EMF, we will draw sine curve. This curve is for EMF. For current, we will draw cos curve. So this is basically the cos curve. So this is I naught. This is for current I. And this is time. So this is sine curve, the curve for the current and for the EMF. The next thing is some discussions on capacitive reactance. Discussions on capacitive reactance. So the capacitive reactance Xc is 1 by omega C. So if I draw omega versus Xc graph, can you predict the shape of the graph? Will it be straight line? No, not parabola. Curve. This particular curve is known as hyperbola. The shape is hyperbolic. So if you increase omega, then your Xc will decrease. But instead of omega, if I ask you to plot Xc versus 1 by omega graph, then see Xc is inversely proportional to omega. But if I'm taking 1 by omega as a variable, if I write 1 by omega is equal to some variable y, then your Xc will be y by c. Xc will be proportional to y. Then your graph will be a straight line. Xc versus omega is hyperbolic, but if I'm taking 1 by omega as a variable, then your graph will be, relation is linear, your graph will be a straight line. And if you want to calculate slope here, here you won't get anything from the slope, but if you want to get slope here, slope is tan theta. Tan theta is here perpendicular upon base. This perpendicular is parallel to Xc, base is parallel to 1 by omega. So this Xc is 1 by omega. You can take that omega in the numerator, so that's omega into Xc. So if you look at here, Xc into omega is 1 by c, it's 1 by c now. So the slope is 1 by c. Okay, so the last thing. Behavior of capacitor for first high frequency AC. High frequency AC. See, Xc is 1 by omega c. Now, Xc is not directly proportional to omega. It's basically inversely proportional to omega. So, if your omega is large, that means your Xc is small. Omega is large, that means your Xc is small. If your angular frequency is large, that means your Xc is small. Capacitive reactance is small. If Xc is small, that means it will allow to pass. Your I is E by Xc. That means your I is large. It's inversely proportional to Xc. So it allow high frequency. But instead of high frequency, if I give you low frequency, your Xc is 1 by omega c. If I take omega to be small, then they are inversely proportional. Xc would be large. If your Xc is large, then your I is E by Xc. If Xc is large, that means I is small. That means a very small current will pass for a very high frequency. It does not allow low frequency. And if you put DC here, for DC, omega is 0, your Xc comes out to be 1 by 0, that's infinite. Infinite obstruction means your current E by Xc, your current would be 0. So it will simply block DC. So if you connect a capacitor with a DC supply to a cell, this capacitor will block DC. It will not allow that DC to pass through it. This is it.